Okay, welcome. Today we are going to have the second discussion session. Tomorrow we have the exam, as you know. And what we are going to do today is to go over the questions that we had in the midterm exam. And we will solve them one by one in the same order that they are in the exam paper. If you have any questions, please raise your hands. If you also, whatever question you might have about the exam, please also ask. And yeah, I mean, logistics of the exam, etc. Yeah?
How relevant is this to the final exam? Because we were told that you can focus on the second half of the lecture.
Yeah, I think it's very relevant because this is still part of the course. There might be questions that are similar to these ones, or questions that were part of the knowledge that you need to solve these questions is still there. And also because it's good that you see the way that we solve the questions, the way that we reason. This also will help you to figure out the way that you have to think in order to solve the questions that you will find tomorrow. Does it make sense? Okay, cool. Minesh is going to be the first one. So, cash forward engineering question. Wait, what? I have.
Microphone is not working.
No, that's not working. No problem. But you might want to use the other one.
Yeah, it looks like it's
Anyway, this one works. So let's use this one.
this one you're saying? Oh. Yeah, definitely works. Okay. Hello? Yeah. Okay, so we're going to start off with, so this is a relatively straightforward question. And so this one's called cache forward engineering. So I'm going to go through the question and then just show quickly how we might solve it, right? So in this question, we're considering a processor with the provided configuration here. So it uses in-order execution, and we have a single L1 data cache that is fully associative and has a capacity of 2 cache blocks, right? So if we're going to draw out what the blocks look like, that means that we have 2 different ways here, and there's 1 block in each, right? So it's quite simple. And another thing is that it has a programmable replacement policy to choose between LRU and Bilaty's algorithm. So the system configuration looks something like this diagram, right? And so there's 2 main paths by which we can access memory from the CPU. One is through the L1 data cache, where you get a miss latency of 30 cycles and a hit latency of 10 cycles, right? So that's represented from the CPU to the L1 to DRAM by this top path here. And then the second one is by directly accessing memory, which results in an uncached access. And this has a fixed latency of 25 cycles, right? And so we say that, note that this type of access will bypass the cache entirely, right? So we're not going to affect the state of the L1 cache at all. So in this question, we're saying that only 1 path may be used at a time, and all memory accesses are serialized, right? So there's really no memory level parallelism here. And so we're interested in optimizing the execution time of this piece of code here, where loading block sub n represents a load to cache block address n, right? So in this piece of code, we have 3 different load instructions here, block 1, block 2, and block 3, right? So these represent address 1, block address 1, block address 2, and block address 3. And so down here, just for convenience, we have the access pattern that this application results in, right? And so it's organized in row major format with 1 row per loop iteration, just for simpler understanding, right? So the pattern is essentially we go through block 1, then 1, 2, then 1, 2, 3, then 2, 3, and then 3. And if you simulate this for loop execution, you'll see that this is the pattern that we have, right? So in this system, we have 2 degrees of freedom available to optimize for. And so we may either replace any of the 3 load instructions with uncached load instructions. So that would be either load 1, 2, or 3. And so we could make it use the non-cacheable path instead. And the second degree of freedom is that we may choose between LRU and Belady's cache replacement. And so the next page kind of describes a little bit about what those are, right, in case you don't remember. So the LRU replacement policy evicts the least recently used cache line, right? And the Belady's replacement policy evicts the cache line that will be used furthest into the future. And so Belady's, in some sense, is an optimal algorithm, right? Okay, so your task here is to determine the best performing configuration, right? So we're given a table with different uncached load instructions. So if we, for example, for none, we don't replace any of the current load instructions with uncached ones. And for the other rows in this table, we replace load number 1, load number 2, and so forth. And so for the LRU configuration and Belady's replacement, we're asked to fill in the cache miss rates and then the latency for each iteration of the for loop, right? Okay, so the question asks, fill in the following table assuming steady state operation, right? So we're not concerned with cold cache misses here, just conflict misses. And we will need to provide the cache miss rate and the average latency of one iteration, right? And so we can assume that the execution time is dominated by memory accesses such that there's no memory level parallelism, and the overall application latency can be computed directly from the memory access latencies, right? So those are the timings that we're given here with a miss latency of 30 cycles and a hit latency of 10 cycles. Okay, and so the second and third parts of this question essentially ask things about the best performing configuration here. So how many uncached loads are used in the best performing configuration, and which replacement policy is used in the best performing configuration? So essentially the task of this problem is to fill out this table, right? And we can get the rest of the question from there. So at first it looks like it's quite a bit of cache simulation, but it actually turns out it's not that much, right? And so I'm gonna go through a couple of examples, and then we'll see that it's pretty straightforward from there on. So okay, so we can just start with the blank sheet of paper. And so the access pattern down here was blocks, this pattern essentially. So I'm going to rewrite it in a format that we can perform a simple cache simulation here, right? So I'm going to put the block address first. And so our block addresses go, 1, then 1, 2, then 1, 2, 3, 2, 3, 3, so forth, and then it repeats again, right? And so since we're asked for steady state operation, we want to go past just the first iteration, so I'll draw one more here as well. 2, okay, and so that's essentially the access pattern we're working with, right? And then so we want to do some simulation of how this works with these different configurations requested here, right? So the first one we want to consider is with no uncached loads and using an LRU replacement policy, right? So if we go through and simulate this cache access pattern, then assuming none, and down here we're just going to keep track of the LRU state, so it's easy to understand. So we'll just call this, I guess, the cache state, right? And this is assuming LRU. So we're just going to go through and simulate the misses and hits here, right? It's relatively straightforward. So for the first one, we have a cold miss, right? And so the cache state will be 1, and then so just remember that the cache looks something like this, right? There's 2 blocks with an associativity of 2. So these 2 blocks will be, 1 here and nothing here. Then for the second one, we'll get a hit. The cache state is unchanged. For 2, we'll have a miss, and then the cache will contain block 1 and block 2. And the second one will be a hit. Cache state is unchanged, and then just going forth and filling out this table, right? So here the second 2 is a hit, and then 1, 2, miss. And so here the replacement policy comes into play, right? So we've missed on the cache block 3, block address 3, sorry. And we want to replace it with the least recently used. So 2 is used here and 1 was used here, right? So effectively 1 is the least recently used. So we go and replace 1 with 3. So we have 3, 2 now. And so 2 is a hit, cache state is unchanged. 3 is a hit, 3 is a hit again. The cache state is unchanged for both of those, right? So that was the first iteration of the loop. And so now we go back to 1. And so this is a miss because it's not in the cache. And so again, we need to figure out what the least recently used is. And so it turns out since 3 is used here and 2 is used here, 2 is the least recently used, so we evict 2 and replace it with 1, right? So the cache state looks like 3, 1. So now we have 1, so it's a hit. The cache state is unchanged. 2 is a miss again, and the least recently used here is 3, so we evict 3 and replace it with 2. And so we're back to 2, 1. So now we can actually notice that this cache state here is pretty much exactly the same as this cache state here, right? Our least recently used is 3, and here the least recently used is effectively also 3 from whatever would have been the previous iteration of the loop. And the cache states themselves are exactly the same. So the same pattern will repeat here for the next sequence of accesses. So we don't really have to simulate any further, right? We kind of just copy paste this pattern here. So we know that's going to be a hit, hit, miss, and then hit, 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 right? And so from this, we can see that in this, which represents the steady state operation now, because this pattern will just repeat over and over, we have exactly 3 misses, right? So our miss rate in this configuration here is 3 out of the 9 different accesses that comprise this iteration, right? So here the cache miss rate is effectively 3 out of 9. Okay? And so now for the latency, we simply use the numbers that were provided in the first part of the question, right? So we have a miss latency of 30 cycles and a hit latency of 10 cycles. And since everything is fully serialized, and the question specifies that the overall application latency can be computed directly from the memory access latencies, we just take the number of misses and hits and multiply by these number of cycles, right? So here we have 3 misses and 6 hits, right? So if we compute what that turns out to be here, it ends up being 150 cycles, right? So this is 150 cycles per iteration. Okay? And so now for the other configurations, we simply do the same thing again, right? And so I'll go through the Belades example as well here. And so now we're going to do the none with the cache state being Belades. And so we're going to go through and simulate this configuration, right? So again, the first one is a cold miss. Then this will be a hit because 1 is already there and the cache state is unchanged, right? So same with 2. This, we're filling this in, and then hit, right? The cache state's the same for these. So 3 is where we get the first conflict, right? So well, it's a cold miss, but we have to evict something. And so this time we evict based on Belades' algorithm, right? And so Belades' algorithm says we need to evict the cache line that will be used furthest into the future, right? So here we want to look at our access pattern into the future, right? And decide which of these will be used furthest. So for 2, we're going to use it immediately next, right? So that's not what we're going to evict. The 1 is used quite far into the future, so we're going to evict the 1 and replace it with the 3, right? So our cache state ends up being 3 and 2. So after then, the access pattern looks just like this because 2, 3, and 3 are all hits, right? So we'll have 3 consecutive hits and the cache state will be unchanged. So now when we get to 1, we have to decide, again, which of these will be evicted based on Belades' algorithm, right? And so here, 2 will be used in 2 accesses, whereas 3 will be used in quite a few accesses. So we evict the number 3 and replace it with 1. So the 1 is a miss, and the cache state now is a 1 and a 2, which you notice is different from what the LRU policy chose, right? And so we go and continue simulating, right? So the 1 is a hit, the 2 is a hit, the 1 is a hit, the 2 is a hit. The cache state is the same up until then. And so now the 3, we have to, again, decide what to evict, right? And so the 2 is used next, so we evict the 1. And so we're back to a cache state of 3, 2. So that's a miss. And then the next accesses are 2, 3, 3, which will all be hits, right? So from here on, the pattern, again, repeats. And so here we see that we only have 2 misses, right? And so this cache miss rate here is 2 out of 9. And the latency that ends up being the case here is 130 cycles per iteration. And yeah, okay. So that's essentially just the first row, right? And we actually have to fill out all the rest of the rows. But it turns out that the rest of the rows are much easier. And so just to see why, we'll simulate one more configuration, which is this one. And so here we have number 1 is an uncached load. And so we'll do the LRU policy, for example. So we're going to repeat exactly what we did up here, except this time, since the 1 is uncached, it does not affect the cache state, right? So the first one, we don't even cache at all, and the cache is completely empty still. Same with the second access. So the 2 is our first miss that actually begins to affect the cache state. And so we're going to have 2 in the cache now. The 1, again, is uncached, so the cache state is unaffected. The 2 will be a hit because it's already in the cache, no change to the cache. The 3 will fill up the second slot in the cache, right? So it's a miss, but now our cache is populated by 2 and 3. From then on, the 2, 3, and 3 are all hits, right? Because they're all in the cache, and then there's no change to what's in the cache. So 1 here, previously it wasn't in the cache, right? But now it's uncached, and so the cache state, nothing happens to the cache essentially. We don't evict anything. And so for all of these ones here, we do nothing. For the 2, it is still in the cache, so that's actually a hit, right? And for the 1, again, there's nothing. The cache state is unchanged. And for the rest of the accesses, they're all hits as well. So we have another 5 hits here, right? And so that completes an iteration. And because there's only two cache blocks that are being stored in this cache, which is of size 2, we never have to evict anything going forward. And so this actually results in a miss ratio of 0, right? So our cache miss rate here is 0 out of 9. And we can compute this latency per iteration. Now we have to take into account the uncached path, right? So the uncached has a fixed latency of 25 cycles. And so we have 3 types of accesses here, right? We have hits, we have misses, and the uncached ones. And so just multiplying those numbers, just like we did for the previous case, we find that this is 135 cycles per iteration. And actually, at this point, we don't have to do any more cache simulation, right? Because the case is exactly the same for everything going forward. At this point, we only have in this case, we only have 2 cache blocks that are stored in the cache. For these cases, since we have 2 uncached instructions, there's only 1 cache block stored in the cache. And for here, the cache is entirely unused, right? So the cache miss rate doesn't even apply here. And for all of these, it's just 0 out of 9, right? Because you never miss in the cache. And so our challenge then is just to fill out these latencies per iteration. And since we know everything is either a hit or it's an uncached access, it's quite straightforward, and we can just go through and compute what those are based on how many uncached accesses we have and how many hits there are. So in the end, it ends up looking like this, right? So here we have a bunch of different access times, and the latencies per iteration actually increase as we go down because we're incorporating more of these slower uncached accesses, right? And so at this point, we filled out the table, which is essentially the solution to the problem. And so the questions afterwards just ask about our configuration here. So how many uncached loads are used in the overall best performing configuration? So we go consult our table here. And the best performing configuration is the one with the lowest latency per iteration, right? And so out of all of these, it ends up being this guy right here. So how many uncached loads do we use? Well, in this case, we're using none, right? So the answer here is just 0. And for the second part of this question, the third part of this question, we're asking which replacement policy is used in the best performing configuration. And for this example, it's Belades replacement, right? So the answer here is just Belades replacement. Okay. That's the solution to this problem. So were there any questions about it? Yeah.
Do you expect any explanations in the second report?
So it's up to you, actually. Yeah, so not necessarily. So if you get the right answer, then it's correct, right? It didn't specifically ask you to explain. But if you're not sure, you can write an explanation there why you assumed the numbers you did, for example. Right, so for example, if you looked at this diagram and you got a little confused whether, say, this is a round trip latency or not, right? Because it's a little ambiguous from this diagram. You could just write that here as your assumption. And then when we're going and grading your question, you'll have a different number than what our solution might say, but it might make sense, right? And so in that case, you'll be fine. Yeah. But so sometimes it'll ask you to explain why. And in that case, yes, you absolutely have to. Okay. All right. Okay, cool. Thanks. Then we'll move on to the next question presented by John.
Put this first so that I will.
Yeah.
Is that right? So yeah, this is the second question in the exam. So for this question, we were given basically access pattern, the addresses, so which are basically in byte fashion. So and the question asks for us like we need to come up with the cache design given those access patterns. So here actually let me explain it first. So basically these are the accesses. So these are the addresses accessed from oldest to young, and then we are given with the hit rates as well.
And also these are the sequences of these accesses. But the important thing is that there are no other address accesses between each sequence. Basically, these are back-to-back. So these are the things that we need to know. And for the first question, basically, we need to figure out for the cache block size. So for this one, actually, we can try to do brute force, and then we can try each of the options here. So let's first assume that we have a block size of 128. So if that was the case, then for the first sequence, 0 will be always a miss, right? So this is always a miss. So this is our first miss. But if it is 128, the 4, 8, 16, and 64 will be a hit because this will be located in the same block as in 0. So we have basically here 4 hits, but whereas in the first sequence the question says we have 3 hits because we have 6 accesses and the hit rate is 1 divided by 2. So this won't work. So let's try 64. For this one, again, 0 is a miss. And again, for 8, 16 will be a hit. 64 and 128 will be misses. So this kind of works. Okay. So let's try 32 again. So 0 again miss. So 4, 8, 16 again hit, and the rest again are misses. So this also works kind of for now. And for the last option we have 8 and 16, but for these see that okay, well, 0 will be again miss for both of these, and but for both of these, actually, we won't be able to include 16. So basically, we will end up with at most 2 hits. And this is not going to work as well, at most 2 hits. So, okay, so we are in between 32 and 64. We need to look at for the second sequence in order to say that, okay, this is the cache size. So for this one, basically, the hit rate is 5 divided by 8, and so we need to first look at those addresses because we basically are sure that those won't be in the same block when they are first accessed. So for the 8K, this will be a miss. Sequence. For the first 8K, this is a miss. For the first 16K, this is also a miss. And for this one as well, this is also a miss, for sure. So these are all misses. So, but again, then the rest of these need to be a hit for us. Okay. So in order this to happen, basically, our cache size need to be 64. Why? If this was 32. Then basically 63 would be a miss because we don't basically access any address between 32 to 64. So in order this to happen, basically our cache size need to be 64 so that we will also have this 63 as a hit. All right. So okay, then 31 and 63 will be hit for us, but here also 64 need to be a hit. But our cache size is 64. But the thing is that, so you need to get this. Basically, we previously accessed 64. So this is already in the cache. So this is also a hit as well. Okay. So our cache size is basically then 64 bytes. All right. So the second part of the question. So this is basically, we are asked to find out the cache associativity. So we're going to do the same. Basically, we're going to try all of these, like 1 associative, 2 associative. So for this one, actually, we need to consider the total cache size. Okay, it's either 4, is either 4 kilobase pairs or 8, right? So for this one, if this is one associative cache, then for the 4 kilobyte cache, all the multiples of 4K address accesses will be will basically try to access to the index of 0, right? And for the 8K, again, it will try to access to the index of 0 if the cache size is 8 kilobyte. So we need to keep this in mind first. And then let's assume that this is one-way associative. And basically write down all the accesses here. Let's write down all the accesses that are multiples of 4K. Okay. So these are basically 8K, 16K, 4K, 8K, and 16K. All right. So if this was one associative, so for each x-axis we would be replacing the index, basically index block, right? So but remember that I'm going to show it here. So those things, these x-axis, need to be a hit in order to have 5 hits, basically, right? So it cannot be one way. So because those will be removed if it is one way, right? So basically, when I access 8K, it will be replaced with this one, and 16K replaced with this one, 4K. And again, when I access the 8K, this will be basically a miss, and then I will basically replace 4K and then put the 8K. So let's imagine two-way. Then the ways are either 2 kilobytes or 4 kilobytes, right? So basically, I'm going to consider all the accesses of the multiples of 2 kilobytes here. Again, I'm going to do the same thing that I did here. So the multiples are basically the same: 0, 8K, 16K, 4K, 8K, 16. I think I need to write more. 32K. And 8K, I guess. Yeah. Right. This was one. So this is actually, the explanation is kind of similar to the one that I did here. So for the 4-way, actually, you can also consider 63 here. 63 will be a miss as well, because I'm gonna replace 0 with 8K, and then 63 will be a miss, and then this will again reduce the number of hits here. So for the 2-way, it's kind of similar. Again, these are the excesses, and for 2-way, actually, I will have this one and this one for the first 2 excess, and then I'm gonna replace 16 for either of these, and then again replace 4K for either of these. So this will make us, like, for sure 8 or 0 will be gone, basically. Actually both of them, right? So so when I try to access 8 here, so this won't be in the cache. So this will be a miss again. All right? So 2-way doesn't work as well. And one-way also doesn't work. So let's look at 8-way. So I'm going to write all the... So for 8-way, then the size of each way is basically either 512 or 1K, depending on the cache size. But basically, we don't know it yet. So each way is 512 or 1K. Then given this, I'm going to basically write, again, all the accesses that are multiples of 512. So these are, again, 16K, 4K, 8K, 16K, 32K, 1K, 8K. So basically, what I did was, so I picked all the excesses in order 0, 8K, 16K, 4K, 8K again, 16, 32, 1K, and this is also a multiple of 1024 and also 8K. So these are the excesses that will map to the same index in this order. So if this was a 8-way, then this would be in cache. Again, this would be, so this is again in cache. So this is already in cache. This is already in cache. So this will be again, that there's a space to put it in the cache as well. So there is also still a space to put this 1K address access into a cache, and also there's a space to put 3K into the cache again, because this is a 8-way associative cache, and all of these actually have the same index basically. So what does it mean? It means that, so if you consider the sequence tree, so our hit rate is 1 divided by 3. So then this means that I only have 2 hits. So let's first find out the first hit. That is for sure will be a hit, which is 129. Why? Basically, the reason is I already access 128 here, right? So when I try to access 129 here, so this will be for sure a hit. Okay. So then we shouldn't. So the options are basically either of these, just one of these should be a hit, not multiple of these. All right. But see if this is a 8-way associative case cache. Basically, I will end up with having 8K as a hit, because this is already in the cache previously, all right? So again, 8-way won't work for us. So then 4-way is our only option left for this one. So the cache size. So we know that this is a 4-way and block is 64 bytes. And we are asking if the cache size is either 4 or 8 kilobytes. So here then the ways are either 1K or the 2K of size, right? The size of the ways are either 1K or 2K, given that cache is either, the cache size is either 8K or 4K again. So then what we need to do is basically, we need to consider actually all of the sequences, but we're gonna focus on the third sequence. So let's again write down all the sequences, the addresses that will map to the index 0, which are basically the multiples of either 1K or 2K. So those will be again. So we are doing kind of the same thing again and again. This is 0, and this is 8K, 16K, 4K, 8K, 16, 32K. So here comes the trick basically. So 1K and 3K will map to the same index if the size of the way is 1K. Basically, if the cache size is 4 kilobytes. So this is only possible if the cache size is 4 kilobytes. Okay. So this won't be possible if the cache size is 8 kilobytes. So because it won't map to the index 0. And for 8K, again, it will map to the index 0. So, okay, we know that this is 4-way. Then this will be in cache. This will be put in cache. And then this one, and this one. All right. So, yeah, all the ways for the index 0 are full in the cache. So 8K, again, it's in the cache. 16K, it's in the cache. So 32K. So for the 32K, actually, we're gonna, I forgot to write down 0 here. There's also 0 there after 32K, there's a 0. So even if the replacement policy is FIFO or LRU, in either of the case, we're gonna replace 0 for this one, right? So for the 32K is not in cache, and then those are in cache, and then I accessed 8, 16 recently, and also 4K recently. So basically, this is the least recently used, and also this is the also first one that put in the cache. Basically, I'm gonna replace this. So this won't be in the cache, and 32 will be in the cache. So for 0, again, this is not in the cache, basically. So what we know is that 0 is for sure a miss, okay? Because remember, we were saying that the number of hits are 2, and 129 is a hit, and then is either 0 or 8K will be a hit for us, and then we now figured out that 0 is also missed, and then 8K, this one have to be basically a hit. So this will be crucial for us in this question. So why is the case? Because if the cache size is 4 kilobyte, basically this is not in the cache, and this also maps to the index of 0. So basically, I'm gonna basically remove this one or this one. So either of these, if this is FIFO or LRU, the either of one will be removed. So 1K will be put, and for the 3K again, I'm going to replace either 4K again, because this will be the least recently used. If it is not 16, let me see. We access 8K, 16K, 32, and this one. Yes. So 4K, either 4K will be removed, or 16K will be removed. So basically, what this says is that if the cache replacement policy is FIFO or LRU, basically 8, this 8, the address of 8 will be removed along the way. Okay, this won't be in the cache. So why this is important? So if the cache size is 4 kilobyte, and this means that we will have to replace the address of 8K, and then this will mean that the 8K here will be a miss. So this shouldn't be a miss. Why? We are already given with the hit rate, and our only option is 8K should be a hit, and then this means that cache size should be a 8 kilobytes, so that those one won't map to the index of 0 in the caches, okay? Not index of 0. So that I will be able to access 8K. So this looks a bit tricky, to me at least. So the last question. So we know that the cache size, is 8 kilobyte. So we know that the cache size is 8 kilobyte. It's 4-way associative, and the block size is 64 bytes. All right, I got through, I guess, yeah. Yeah, let's do the same for the one last time. So I'm again writing all the address accesses that will map to the index of 0 in a sequence. 8K, 16K, 32K, 0, and 8K. And this is 4-way, right? So those are all in the cache. And if it is, this is 8K, this is in the cache. But if it is LRU, then this is the one that is recently used. So 8K in the cache, 16K in the cache. 32 is not in the cache. So basically, I'm going to replace 0 for the reason that I just discussed in the previous question. So 0 will be replaced, 32 in the cache. So for the 0, so if it is FIFO, then we will have to remove 8. Again, but for the same reason that I described here, 8 should be a hit, then this shouldn't be a FIFO. This should be, the replacement policy should be least recently used, so that I won't remove 8K. Instead, I will remove 4K because this is the least recently used. Okay, and then this will be a hit. All right, then the policy is LRU. All right, this was mostly oral explanation rather than writing everything here mathematically, but I hope that was clear. Is there any question? All right, I guess none. So yeah, we can move to the next question, I guess. This is Minesh, by the way, Minesh.
Okay, so this question is relatively easy. I think most of you did this correctly in the exam, except the last part maybe, which is also simple, but looks a bit more difficult. Yeah, just to remind you, so I will just highlight the most important parts of this question because the text here is so long. So it's basically like asking you what will happen to those read requests here, like in terms of latency and like how the system that they are executed on behaves. So basically you need to like look at those requests here, which are all read requests to some like specific physical addresses. And then you have the command types that result based on execution of these requests and the state of the system. So you need to figure out basically what's happening, right? So there's some like reverse engineering that has to be done. So basically in this, like in those physical addresses, we can figure out exactly to which bank and to which row they go based on the information given in the question. So we have a single channel, so we don't care about channels. We have 2 banks and 64 rows per bank, right? And then here we have important information, which is telling us that the most significant bit of the physical address gives us the bank that will service this request. And then the following 6 bits of the physical address determine the row. So basically, if we like write this in binary format, which is like, is this correct? Yeah. And then 7 is this, right? So we don't have to write all of them because we need only the most significant 7 bits to figure out what is the bank and what is the row, right? So for example, here, by looking at those in like binary form, we can easily tell that the bank is 1. So for this request, it targets bank 1 because the most significant bit is 1, and then the next 6 bits here are 43. So the row is 43. So we have to do it for each single request here. It's not too much work. So this is this, and then this is 8. Oops. This is 110, and then 4, 001, and then 8, right? Yeah, so if you do the same here, so for the bank it's very easy, right? So the bank is just, the second request is bank 0, third request is again bank 1, and then bank 0. Okay, and for the row, we look at the next 6 bits. So here it is 20, those bits, and then the next request also, it goes to 50, and then the next goes to row 20. Okay, and basically, if you look at those commands here, so we see that the first command that the memory receives is read, right? So it means that for the requests here, we have the row already open, right? Okay, so and here in this text here is like given necessary information that you don't know the initial state, right? So since the first command here is read, we can tell that bank bank 1 had row 43 open. So I'll just write it like this. So we can figure out this information, right? And then the next command is precharge. So since this comes right after the next cycle, so this could be either precharge for precharge to again bank 1 or bank 0, right? But since it comes right after the next cycle, it's more likely to be a different bank, right? Because I mean so we know that usually there's some like latency between like read and precharge operations, and hopefully it's more than one cycle. So here, yeah, we can assume that this goes to bank 0. So the next precharges. So we are precharging bank 0. So since we are precharging here bank 0, we know that bank 0 bank 0 had a row open, right? But we don't know exactly which row was open. So, but we know that it was not 20 at least, but we don't have any other information. So this is relevant to one part of the question, which is part B, but we can like do it like based on this information that we figure out. We can just fill this part, right? So we know that both rows are open because for bank 0 we had to precharge the row, and for bank 1 we service the read request, right? So the initial state is open for both, but bank 0 had 43 open, but for bank 1, bank 1 was 43, and for bank 0 we don't know which one. The only thing we know is it wasn't row 20, right? Okay. Okay, so if we continue here, we can figure out more information. So for example, here at cycle 8, we get a precharge command, right? So we already precharged bank 0, so this is guaranteed to be bank 1, right? And then since this is bank 1, and we waited for exactly 8 cycles here to issue a precharge, we know that the timing parameter here between read to precharge is 8, right? So this here, let me use a different color. So this is 8 here. So yeah, read to precharge latency is 8 cycles. So we have the frequency given here. It's 1 gigahertz, which translates to 1 nanoseconds per clock cycle, right? So if you have 8 cycles here, we can fill it in here, right? So it's 8 nanoseconds. So here in part A, if you remember, it asks us to fill in the timing parameters in terms of nanoseconds, yeah. So here, or right unknown. Okay, so we figured that out, and then we have an activate here. So since we first issued a pre-charge to bank 0, this activate is also bank 0, right? So since we started this pre-charge later, it cannot complete before this pre-charge. Okay, so this activate is bank 0, and we are activating for this row over here, right? So we are activating bank, row 20. So this is also telling us what is the distance between like pre-charge and activate, right? So it is like 12 cycles here. So the pre-charge to activate latency is 12 nanoseconds. Okay, so let's continue. Then we have a read. So the only active row we have is bank 0. So this is like access to bank 0. So basically, we are completing this request over here, right? So we already completed this one with this read. So now we are completing this request here. So the activate to read latency here is 5 cycles. So we got that too. Yeah, activate to read latency. This is 5 nanoseconds. Okay, and then we have another activate. So here again, we can see that pre-charge to activate latency is 12 cycles, right? And then we have read. Again, this is okay, so this read, okay, so this part is interesting. So we have 2 identical requests here to bank 0, right? So they both target the same row, but different columns of that row. So while this is being activated, so this activate is bank 1. While this is being activated, we can service this last request from bank 0, right? Which also targets row 20. So basically we have row buffer hit here. So this is telling us the distance between 2 read commands, right? Which is 4 cycles here. So read to read latencies 4 nanoseconds. Okay, and then we basically complete by servicing the last read request, which is here the third request in this order here. Okay, so one thing that we cannot figure out here in this table is the second part, activate to pre-charge latency. So this is unknown, right? And we cannot tell exactly what is that because we never see here in this like command trace, we never see activate to pre-charge, right? So we have pre-charges here, but we don't know exactly at what point activate has been issued to that bank, right? So we cannot tell exactly what is the latency. Maybe we can bound it a little bit, right? So it is, yeah, we can't even bound it, I think. Yeah, so it's unknown. Okay, so is this part clear? Okay, I guess so. And the next part is about TL-DRAM, right? So if you remember TL-DRAM from the class, basically it is dividing a subarray into 2 parts, into like fast region and slow region. And this table here is giving us how the access latency, how those like timing parameters change when you are accessing the fast or slow region, or near and far segment. The far is the slow region, right? Yeah, and the question is basically giving us the number of cycles that take to execute these requests here. If you have a TL-DRAM where the near segment, the size of the near segment is defined as n-1, right? So the rows from 0 to n-1 are in the near segment. So we don't know what is n. And the rest are in the far segment. And then the question is telling us that with some value of n, it saves 2 cycles in the overall execution time. So previously, we completed those 4 requests in 25 cycles. Now with TL-DRAM, for some like specific value of n, it completes 2 cycles earlier in cycle 23. So we need to figure out basically what is the n here. So there is an so how you should approach this problem is you can easily eliminate some values of n, and then you can like check much smaller number of them. So if you look at here, so we kind of like reverse engineered here the banks and rows, right? So we have only a few ranges here. So we have like rows from 0 to 20, right? That like could cause a difference basically. So all values from 0 to 20 are equal, like in terms of, so they will all result exactly in the same execution time when we use TL-DRAM, right? Because we don't have any rows in between. Okay, so the ranges we have to check for n is like one value between 0 and 20, and then one value between 20 and 43, and then 43 to 50, and then more than 50. But here, so we can easily eliminate some ranges, right? So we know that it completes to cycle faster. So we can easily tell that so we shouldn't have all of these rows that are accessed here in the far segment. Because if that's the case, we cannot save any latency, right? We will have some overhead. Okay, so we don't have to check the case where n is smaller than 20, right? So we only have to check other regions here. And if you just go in order, I think you will figure out that the range from like 20 to 43 doesn't work. So you get something, I think, bigger than 2 cycles here. And then if you evaluate for n, where n is bigger than 43, so it's like bigger or equal to 43, and then smaller than 50, right? So we have those 2 rows, row 20 and row 43 in the near segment, and row 50 in the far segment. We get exactly 2 cycles of execution time saving here. And then what you need to do is basically, for those ranges, basically redo what will happen to how those requests will be serviced, basically. Because you know everything you need to know to like run the simulation, right? So you know the initial state, you know the request, which banks, which rows that they target, and based on that you can like simulate a new command trace here. And yeah, basically once you do that, you will like see that this works fine, and it gives you exactly 2 cycles of latency saving. Okay, I think that's it. We don't have part D. Do you have any questions? No? Okay.
Okay, I think we can start. Are we already recording? Okay. So next question is DRAM refresh from the midterm, and I think for most of you it was pretty straightforward. So I'll just go over it very quickly. So in the first question, we are calculating the memory bus utilization for the refresh operations. So here we have 2 to the 15 rows, and we are refreshing them one by one. And at every refresh operation, the bus is busy for 5 nanoseconds. And we have 8 banks here. So the first question asks for the utilization, and it gives that refresh interval is 64 milliseconds, right? So what we do here is pretty straightforward. Command bus is utilized for 8 banks, 2 to the 15 rows, and for 5 nanoseconds for each row at every 64 milliseconds. So when you just compute this and divide it by 64 milliseconds, you get this number. So as far as I remember, a common mistake in these kind of questions was you guys calculate the hard part, and then when it comes to this calculating this percentage, like you just need to divide this to 64, right? And you just don't do that, and you lose some points. So don't do that. Just read carefully and answer every question asked. So in the second one, we figure out that some of the rows can actually hold the information for a longer time, and we can refresh them at every 128 milliseconds instead of 64 milliseconds. So the percentage of those rows is 60%, right? It's written here. So what we do here is I look at every 128 milliseconds. For this 60% of the rows, I need to refresh them only once. And for the remaining 40%, I need to refresh it twice in every 128 milliseconds. So it's the same calculation actually. You just calculate utilization based on this. Actually, you just add up these numbers here and then divide it by 128 milliseconds, and then you get this number. And then as a second part of this question, it asks you to calculate the reduction based on the first question, right? So this was one of those mistakes that I mentioned earlier. You just calculate this and then you don't do the reduction and you lose some points. Don't do that. So here what I do is, this is our new value, right? And this was our old value from the first question. And you just normalize it and then get the reduction value. So the second part of the question is a bit more interesting. So this is based on a paper published in 2018 DAC. It's variable refresh latency. So the main observation in this paper was, as we described in the question, is you don't have to wait for the full refresh latency. So what is refresh latency? So okay, so this is your time axis. I'm just drawing this for one single row. So this is your refresh interval, right? This is just some extra knowledge about this question. And this is your refresh interval. And when you start the refresh operation, it also takes some time. This is refresh latency. And this paper tries to mitigate this refresh latency, and the main observation was that you can actually get a pretty good restoration in the voltage level if you just wait for the 60% of this latency instead of waiting the whole thing. So the remaining questions are going to be based on this observation. So in the first one, the question tells us that here we see a graph. On the y-axis is maximum number of partial refreshes. So when we just use 60% of refresh latency, it means a partial refresh. And we cannot keep doing this for the whole refreshes. So this plot means, as described on top of that, if I see a value 1 here, then it means that after a full refresh, I can do only one partial refresh, and the second one should be full refresh again. And if it's 3, I do a full refresh, and I can do 3 consecutive partial refresh for the other 3 refresh intervals, and then I need to go back to full refresh again. So this is how this works. And here, what we need to calculate is how much time does it take for a bank to refresh all rows within a refresh interval, right? So here we only have one single refresh interval, which is 64 milliseconds. And our refresh latency is, the full refresh latency is described as T, and the partial refresh is 0.60, the 60% of that, right? Okay, so what we do here is actually just multiply and add them up. So here, as you can see, like 10%, 60%, 30%, this is the whole distribution of these rows. I can, for the 10% of the rows, I need to fully refresh those every other interval. So it's like interleaves between partial and full refreshes. And for 60% of them, I need to fully refresh them after every 3 partial refreshes, right? So what I do here is, this 0.1 comes from 10%, and then half of them should be partial, half of them should be full, right? And for this one, 60%, 0.6, And then 75% of the refreshes should be partial, and 25% should be full refreshes. So I just calculate these, and then add them up, and then it gives me the refresh latency of a bank as this value. So I hope it's pretty clear now. And a lot of people already found this exact number in the exam, so I just assume that it's easy. But if you have questions, you can ask anytime, interrupt me. Okay. So based on this observation, we need to understand like what is our benefit here in this paper. So for that, we need to come up with a good baseline, right? So in our baseline, we see that 90% of the rows can be refreshed at every 128 milliseconds. And 10% of the rows can be refreshed at 64 milliseconds, right? So here what we do is we want to compute the refresh overhead of the baseline where we don't have any partial refreshes. So here I have the value for a single refresh command, which is this, where n is the number of rows in a bank. So refreshing the whole bank is going to take 0.2 milliseconds, right? Okay, so again, I do the same thing that I do in this second part of the first question in the basics. Remember, it was like 60% was being refreshed once in every 128 milliseconds, and the 40% were being refreshed twice. So it's the same story here again. I just look at every 128 milliseconds, 10% of the rows are refreshed twice, and 90% is refreshed once. So when we just add them up their costs, we see that the bank is occupied for 0.22 milliseconds for every refresh. And this every refresh happens at every 128 milliseconds, so refresh overhead is this number here. Okay? So this was our baseline and the answer of this question. And the last part of the question is here. So here we are merging these, like on top of the baseline, we want to add partial refresh. And in the partial refresh, we have another plot here. So here we have two refresh intervals, one for 64 milliseconds, the other one for 128 milliseconds. And the y-axis is the same as before. So here you can see that when we add all these up, it goes to 100%. So this is the distribution. And okay, so let's start with this 128 millisecond ones. So here I refresh all these rows. I mean this 20%, this 65%, and 5% at every 128 milliseconds, right? And for this 20%, it's always full refresh. And for this one, it's one full refresh, one partial refresh. And for this one, it's 3 partial refreshes and 1 full refresh. And then for the 10% of them, I need to refresh them at every 64 milliseconds. And it should be one full refresh, 1 partial refresh. So just by following the same method, we can see that at every, so you can choose whatever value you want here. I just choose 4 times 128 milliseconds because it makes the calculation much easier. You can go for another value. It's up to you. And you can see that for every 20% of the rows, we refresh this 4 times. And then these 4 refreshes, all of them are full refreshes, and none of them are partial refreshes. And for 10%, I refresh them 8 times because this was 64 milliseconds in refresh interval. And half of them, I mean the four of them full refresh, 4 of them are partial refresh. And you just go like this. And then when you just convert these text to mathematical representations, then you get these equations here. When you just add them up, you can easily reach to at least up to this point. You should be able to reach very easily. It's very straightforward math. And then, yeah, if you compute more, you can get these results. But you can just take this equation and say it x or, I don't know, a, something like that, and then compute the rest of the thing just by using that parameter. And as mentioned earlier, you don't have to compute the final exact value in the exams unless it's explicitly stated in the question. And you need to answer all the questions you see in the text, and you need to show how you get those numbers. We should just see your method, how to retrieve them. Okay, so this was the DRAM refresh question. Do you have any questions? Comments? Okay, I think that's all. And we are going to continue with Mohammed with GPU question.
All right, guys, so the next question about the GPU and SIMD. So basically, you are given a piece of code, and you are asked to analyze the SIMD utilization and how many warps does it take to execute this program. So the question gave you, so basically per warp, you have 64 threads. And the question said that per iteration, you assign each thread to each iteration for that piece of code. So you have this much of iterations, then the number of warps, or yeah, the number of warps basically equals to the total number of threads you need to execute this program in parallel over the capacity that warps provide you, which is number of threads per warp. So you have 4096 over 64, which give you about 64 warps. So this question is straightforward. However, if this fraction is not divisible by 64, normally we take the ceiling, because you cannot leave part of those threads unless they are inside a warp, then you are utilizing that warp as well. For point B, we want to measure the SIMD utilization, and the definition is given in the question. You can think about it as the number of instructions that basically or actually used by the thread over the number of instructions that at most use during the entire program. So the SIMD utilization is given here in this point, and you need to comment about the value of A, B, and C, or those arrays. So basically, the SIMD utilization here is not affected by the value of A and C. Why is that? Because the if conditions here depends only on the value of B at that index, which is I. So here it won't be affected, and as well as in C. So for part B, or for array B, so you are given the actual number of instructions used over the number of total instructions used for that many of threads per warp, which is 64. So for this type of question, you need to analyze basically this piece of code and see the branch divergence. So basically you have two blocks, and you need to be careful about the if conditions here. So here it's not if else, it's two if blocks. So basically either you visit the first one or you don't visit it, and for the second block as well. Either you visit it or you don't visit it. So to enumerate those possible values, so in the first block, you have the if condition, so you always visit it. You always need to check the condition, whether you met it or not. And inside that block, you have another extra 3 instructions. So basically, you have 4 instructions coming from the first block, if it is executed fully. And the second block, you have 2 instructions. The first one is the if condition, and the second one is the instruction inside the block. So for this, per warp, again, it's given by the question that we have 64 threads. So basically, you can think about it. Either we have 64 multiplied by. So if we visit the first one for all those many threads, then we have 4 instructions. For the second block, this for sure we will visit it. We execute that instruction because it's if, it's not if else. So we have 1 here. So this in case we didn't visit or the condition here is false. So we cannot execute the internal instruction. And for the second case, so you have again 64 threads per warp. And imagine now the other scenario where you don't, where the condition for the first block is false and the condition for the second block is true. So you will execute the first one plus 2 from here. So now, what if we didn't execute both blocks? So the condition was false for both blocks. So for sure, you will visit the first one to check the condition and the second, and the instruction from the second block, and then you'll have 2 times. So when is this true? When the value here is exactly 8,888. What else we can have? So imagine for some reasons that we execute part of the threads over the first block and the other part of those threads within a warp for the second block. So you will have max of those blocks, where we have maximum branch divergence. So in this case, you will have executing all the instructions at most, which is 6. All right, so here we enumerate all the possible scenarios where depending of course, on the value of b at the index I. So here, let's go back to our question. It gives you the 320, and 320, you need to be sure whether it's coming from this scenario or that or that or that. So apparently, it's equivalent to 64 multiplied by 5. And if you remember from this scenario, what we do is basically we assume that all the data makes the block or the first block to be executed, which means we have this instruction, and then we go inside it, and the 3 of those instructions are getting executed. For the second one, we only execute the first one, but the condition was false, so we didn't continue. Now we need to figure out where does this 134 come from. So basically, as we said, for this case, the first instruction here, actually, let's give them a number. So we have 1, 2, 3, 4, 5, and 6. So we have 6 instructions. So for the first one, it will be executed for sure, plus the 5. So the first one will be executed 64 times plus the number 5, instruction 5 will be again executed by all threads. Plus, now we agree that we always will visit this block. And it has 3 instructions, but we are not sure how many of those threads will go into that 3 instructions and execute them. Again, it depends on the value of B. So we have 3 instructions multiplied by a variable that we don't know yet over this case, which is 5 instructions at most executed by 64 threads per warp. And this will give you the percentage or the SIMD utilization that's given by the question, which is 134 over 320. If you do the math, then X will be 2. What does that mean? Means only 2 threads are able to execute the first block fully, which means that the value of B was less than this much. And the rest of the values does not allow you or does not allow that thread to go through this block or that, which it should be equivalent to 48 or 8,888. So you have only two times per 64 elements of B are equivalent or less than this, and the rest are equivalent to this value. All right. So for this type of calculation we did here, it should apply to the last part, which is D. Anyway, let's continue to part C. The question asks you whether we can achieve 100% SIMD utilization or not. So we know that branch divergence is bad for us, so we need to minimize that. So we can achieve the 100% utilization by allowing all those threads to work in parallel within that warp, which should give you the maximum SIMD utilization by giving the same workload or the same number of instructions to be executed per thread. And when is that possible, basically, is to have the numerator equivalent to denominator. So based on those cases, we cannot have the case where we visit sometime the first block and the other time the second block. Why is that? Because in this case we have the branch divergence, which we don't want it if we want to achieve 100% SIMD utilization. So we left with 3 cases, which is this or that or that. So those 3 cases, either I'm going to visit always the first block, or always the second block, or none of them. And for that, you can infer that the value of B should either be less than this number, or all of them higher than that number, or all of them equivalent to that number. So in this case, we achieve 3 cases where we can have 100% SIMD utilization. So any questions so far? All right, cool. So for part D, now we want to do calculate for the lowest SIMD utilization. And again, this is a fraction number, so it's ratio between 2 things. And to make it the lowest, you need to make the denominator as a maximum in order to have a minimum fraction. So to have the maximum for denominator, obviously you need to go for the first case. The first case where we have some of those threads applies or allow for the first block to be executed, and the other some allow the second block to be executed. So only in this case, we're going to achieve the minimal or the minimum possible SIMD utilization. But we don't know basically how many of those threads out of the 64 allow the first block to be executed, and how many of the other threads allows the second block to be executed. So we have two variables here. And for that, so we know that the first instruction will be always executed. So we have 64 threads executing the first instruction as well as the fifth instruction. So 64 plus 64 plus. And now if some of those threads allows the first block to be executed fully, then we have 3 instructions inside, but we don't know how many of those threads. And then we have 3x plus. Same thing applies to the second block where you have a single instruction. So let's give it a variable y. And we said that we have 64 multiplied by 5. Why is that? Oh, sorry, it's 6. This is the max, or at most, we're going to visit all those instructions. And we want basically to have the minimum. So what value it could be the x or y? So can we have it as 0? Obviously not, because if we ever never visit any of those blocks, the first or the second, then this will be less than that. So at most we have 5 instructions or maybe 3. It depends on which block we allow it to be executed. And so to have a value of 0 here for x or y, it's invalid. Cannot have that. So the next minimum is to have it 1 for both of them. And this basically gives you 64 plus 64, 128 plus 3 plus 1 over 64 times 6. And that gives you 132 over 384. So this is the minimum SIMD utilization you can achieve for that piece of code. Is it clear? Any question? Right. Thank you so much. So next will be Juan.
Okay, now we are going to solve the vector processing question that we had in the exam. Just 1 second. Okay. Yeah, so this is the question, vector processing. In the table you can find the ISA, what are the instructions that belong to this processor. You see that there are 3 instructions that are not pipeline. They are used to, they can be used to load stride, length, and vector mask. And then we have some pipeline instructions for load, stores, and arithmetic operations, arithmetic and logic operations. So all the details about the processor can be found here in this list of points. You can, I mean, you have already read this, so now if you need to go over, you can do it. And like some interesting things that we have to keep in mind is that there is an instruction LDM that create the mask. It will load the least significant bit of a certain vector register for every single vector element in the corresponding position of the vector mask, then it's also important to keep in mind that we have memory with n banks and that n is a power of 2. So the first question, part A, asks us to to be able to figure out what should be the minimum value of n, being n the number of banks. And because n is a power of 2, and we know according to this table that load and stores take 22 cycles, you should know that n should be equal to 32. And why is that? Because if we want to have one output every cycle, we need to have a number of banks that is higher than the latency of the load and store instructions. So because also we have the restriction that n should be a power of 2, then the next power of 2 after 22 is 32. So this is the number of banks that we are going to consider in the, for this, as a solution for this part A. Now let's go to probably the most interesting part of the question, is the rest of this question. And we are given some piece of code, as you can see here. And part B asks to write the assembly code to implement this piece of code. So observe that the vector length is 64, so that's what we are going to consider, and actually is the very first thing that we are going to do is loading the vector length, VLength 64. Next thing to do is loading the stride. That is 1, as you can see in the code. Next thing that we will do is loading A, because we need to check what's the value of A, and we might use it later actually in the else part of the if-else statement. So we load A, we are going to load it in vector register V1, then we have vector register V2 where we load C. We are giving one hint here. C should be loaded only once before evaluating the if statement. So that's why we do it here. And right now, what we are going to do is evaluating what's the value of A so that we create the mask accordingly. And for that, we need to use this compare to 0 vector instruction, and we will store in V3 we will store zeros or 1 depending on this comparison. Remember that in V1 what we have is the corresponding value of A that has been loaded with the previous instruction. Right after that, we create the mask, V mask from V3. So here what we are doing is creating B mask, and now we are able to execute this instruction because we are in this part of the if-else statement, and the mask has the corresponding values. So we start the store in B, array B. We are going to store the contents of vector 2 that already contains the corresponding values of array C. And right after that, what we are going to do is flipping the mask. And why is that? What we do when we flip, so we need to flip the mask because now we want the remaining lanes or the remaining threads to execute the else part of the if-else statement. So what we do is flipping the bits in V3, which was this register here that contained the result of this comparison, and now we load the mask again. And so this could be like the negated value of the mask, right? One thing to keep in mind here, observe that this B0 instruction is not subject to B mask. So we are considering that all the lanes of the vector are going to execute this. And this is something that we have already clarified in the question, and actually we have we have gone over all your answers again, because we wanted to make sure that this question was correctly grading, and now you might want to go to Moodle and check what's your final grade in this question, because in some cases you might see some small increase in your final grade. Okay, so now that we have this mask for the else part, we can do the multiplication. Result will be stored in V4. The source operands are in V1 and V2, and finally we will store in the array B. We will store the output in array B. So now that we have this code, in part C, what we're going to do is calculating what's the total number of cycles needed to execute this program. The vector processor that we are considering, as is defined in the for this first part of the question, is that there is no chaining and there's only one memory port. So this is what we are going to keep in mind when we when we draw this timeline for the instructions as they are executed. So observe, because we have, I will try to put it here so that you can also see what's the code. The first instruction is LD to load the vector length. This will take one cycle. It's not pipeline, so it's just like one cycle. Then we have the next instruction, again, is load for the vector stride, so it's again one cycle, and then we have the vector load that will start right after that. The vector load for the first element will take 22 cycles, and right after that we will obtain one output every cycle. So this is going to be 64 minus 1, that is 63 cycles, right? So and then we will issue the next vector load. The problem here is that there is one single memory port, so we can only start with this vector load when the first vector load finishes completely, and it will take 22 plus 63 cycles again. But one thing that we can overlap in the meantime is the execution of this vector com that can start right one cycle after the second vector load, and it will be something like this. And then, yeah, you have a question?
I assumed in the last exercise, so the B part, that the mask only applies to like the multiply instruction and not the store instruction, I think.
You assume that?
Yeah. Makes sense. I mean, it never was really specified what is mask and what is not mask. Somehow it didn't make sense to me that the store would be.
So, and then the way that you solve this was by delaying the store until the end, right? Just doing one store.
Yeah.
Yeah, okay, yeah. We have taken that into account.
Oh.
Yeah, check your grade. Yeah. Anyway, if you have any other question after that, you can contact me. So, okay. And actually, that's an interesting assumption. It's not clearly stated, but it was an interesting assumption. It's good as long as you. So when you solve problems, as long as you make reasonable assumptions, we always try to be lenient in the grading and considering things that really make sense. And this assumption really makes sense. Okay. So we continue after evaluating this comparison instruction. We have the LDM. You know that it takes one cycle, and then we have the store, VST, and this store should start right after the second load has finished, because recall that we only have one single memory port. So this is 22 plus 64. And now, because the next instruction is independent, V0, it can be issued right after the store. It will be something like this, 4 plus 63 cycles, and then again LDM, 1 cycle, and then vector multiplication that takes 6 cycles, plus 63, and finally the VST, because we have no chaining, we have to wait until this finish. So yeah, this will be 22 again plus 63, and you can count here that the total number of cycles is 395 for this part. Okay? Yeah, now let's go to part D. Now in part D, I'm going to keep the code here so that you can see it. Now in part D, we execute the same thing but in a vector processor that supports chaining. So this means that as soon as one instruction for one particular vector element finishes, it can be, the result can be forwarded or chained to a different vector unit, right? So we are going to take advantage of that. Here again we have 1 cycle and 1 cycle for each of the LD instructions, and then we have 22 cycles for the vector load plus 63 for the second vector load, because we still have 1 single port. We will have to wait until it is completed. But the interesting thing here is that because we support vector chaining right now, this compare instruction can start right after the first operand, the first result is obtained, is read from memory. So it will take 4 plus 63, and right after that we have the LDM instruction. This takes 1 more cycle, and next vector store. And observe that we only have 1 port, so we will have to wait until the second load finishes, and then we can issue this first store instruction. But at the same time, and same as we did in the previous part, in part C, we can overlap with this V0 and 1 more cycle for the next LDM, and finally vector move will take 6 cycles plus 63, and the VST, final VST, can start right after the first result of the multiplication has been obtained, and we can start accessing the memory again for writing. So in total, this will be 322 cycles. Okay? Okay, and now part E. Now we support chaining again, but we have 1 more memory port. So this will allow us to overlap memory accesses. So again, we have load, unload, 1 cycle for each, and the first vector load is 22 plus 63. But because we have now 1 second memory port, we can start with the second access as soon as we issue the first request for the first load instruction. And because we have chaining, we can start the execution of this compared to 0 right after we get the first element of array A. So this would take 4 plus 63, and then 1 more cycle for the LDM instruction. Then we start the execution of the first vector store, 22 plus 63, and then we overlap with the V0 and with the LDM as we did before. This is 4 plus 63, This is one more cycle. And next, vector mul and vector store that will start right after the LDM instruction. This is 6 plus 63, and because we have chaining, we can start the store instruction right here, so it's 22 plus 63. So you will see that the total number of cycles here is 252 cycles. Questions? Okay, and now let's go to the last part. In the last part, we have a more efficient way of implementing predicated execution. Observe that in the original vector processor, the only thing that we check is the value of the mask only when we are going to commit the result. So let's say on the write back stage, we check the value of the mask, and if it's 0, we won't commit the result. If it's 1, we will. But here in this part F, we are told to consider a more efficient predicated execution, that is the density time implementation, that essentially scans the vector mask register before issuing the instruction. And if there are no elements with a non-zero mask, that is, if the mask is 0 for all the vector elements, then the instruction is not issued. And the question here is, okay, what will be the minimum number of cycles, assuming the original processor where we don't have chaining and we just simply have one memory port. So the minimum number of cycles will be obtained when, if you see this code, will be obtained when we avoid the execution of this instruction here, or these two instructions here, these two instructions that actually are the vector mul and the vector store. So if we go back to part C, where we calculated these 395 cycles, we will be saving this and this amount of cycles. And now you can, because actually the last thing that finishes is would be this store instruction. So you can calculate, following the critical path, what's the total number of cycles, and the total number of cycles for part F of this question is 257 cycles. Is that okay? Okay. Any other questions? Okay, so if you don't have any other questions, then we will solve the last question.
Let's not do the last question unless people want it.
Okay.
Come and ask questions. Maybe answer questions. Or do you guys want to take a break? What do you prefer? I can take questions right now and maybe leave early, or take a break and take questions later. Sounds like I can take questions now. Okay. Okay, we'll see. I don't know if I want to project anything yet. It'll depend on your questions also. Okay, it's been a long semester. So there are alternatives we can do. Geraldo can solve the branch prediction question. I'm not sure how particularly useful it will be for the exam tomorrow. I can give you a hint. But if you really want to learn the solution, you can listen to him, or you can ask me questions on anything you have in mind related to the topics. Not necessarily exam questions or anything, but concepts.
More logistic question. Like,
sure, yeah.
What is the time frame of the grading of the different labs and homeworks and so on? Because at the moment it's really hard to figure out where we are standing. Like, it could be,
sure.
Labs could be wrong and be like a really huge problem.
Yeah, that's right. So labs have You started grading the labs, right?
Graded?
Mm-hmm. Lab 1 is graded, I think. Or no?
No, it should be lab 1 to 4. I hope you get contacted by TAs about the grading of lab 1, 2, and 4. At least for lab 1, I'm 100% sure.
Yeah. Lab 1, I've seen the.
Yeah, that one
Yeah.
is.
Okay, so I will remind the rest of TAs.
So I think we should get the lab 2, 3, 4. So it will happen during the.
They are
break.
graded. If they didn't contact you, probably they are thinking about doing it this afternoon.
Okay.
And-
So you have an answer.
I hope that is clear. And for the homework, they are also graded. We didn't release the grades yet because actually there's no possibility of improving the grade, but the solutions are already there. So you can see if you did well or not.
Okay.
But anyway, they will be released. They also be released today.
Yeah, we should release the homework
Once, or when we're back in January. And so for the labs, we would really encourage you to fix whatever is pointed out by the TAs and also do the extra credit because this can be very useful for you for your final grade.
And for learning, I think. I'm more worried about the learning than the grade, frankly. I know the thinking about grades, but this is a master's PhD level course, so. So I think, I think Juan answered that better than I could. Does that answer your question, or?
Yeah, you can just have, I mean, it's not important that the grade is good, but just to have like somewhat of a.
Sure, understanding, yeah. But you can, with the homeworks, I wouldn't be too worried because you have I assume you know that you have all of the solutions, right? I think labs is a bit harder one, but I think Juan will get back to you soon, like today. Any other questions on the exam? We've covered a lot of topics since the last exam. So you can ask me questions on the concepts or other things. Does it help if I go through some of the topics that you covered? Yeah, I think that might jog your memory better. Let's see. I need to project. Let's see this. PC6. Okay, that's better. Now I cannot see what I'm editing. I guess I should mirror displays. Huh? Okay. That's much better. Cool. How do we turn this off or move it down? Okay, I think it automatically does it. Thanks. Okay, so maybe we can look at some topics. So you probably know all about this by now. You were examined on the first exam, and you've been doing assignments. You can ask me questions on those. So what we've started with was introduction, basics, row hammer, computer architecture fundamentals. Then we covered memory hierarchy and caches. And then more caches, advanced cache techniques, some of which you may be implementing, or you may have implemented. By the way, you can still implement. And then we talked about main memory, DRAM, different issues in DRAM, and we had some lectures by the TAs on DRAM latency and retention time, and interesting analyses that lead to a physical unclonable function, for example. And then we switched gears a little bit to accelerators, like SIMD processors and GPUs, and then genome analysis. And then we covered branch prediction, architectural simulation, memory latency, energy and power. Then we talked about processing in memory, emerging memory technologies, and then flash memory and solid state drives. And then we had the exam. And after the exam, we covered a little bit more flash memory, and then we talked about memory interference and quality of service, all of the different ways of handling memory interference. And we focused on multi-core cache management, how cache management becomes harder in multi-core and more important. And then we covered heterogeneous multi-core and more heterogeneity, like GPU programming. And then you had the video lecture on multiprocessors, consistency, and coherence. I don't know why the videos are not linked, but the videos should be here also for the interconnects. If you go to the YouTube, you'll find it. They should be linked also. And then we covered interconnects at the end. Now you have, it's your turn. Any questions, thoughts? Like, are there any concepts that you would like to talk about? What do you think? I assume you guys have started studying, right? Yeah? No topics? Everything is clear perfectly? Should be? Okay. Okay, that's good to hear. And also, homework, last homework that you're doing should be useful for preparation for the exam. I mean, it's obvious. If you do the homework questions well, answer them well, it covers a lot of the topics that are related to the exam, of course, right? So as I said earlier, you can expect more questions on the second half of the course, which is normal, I think. Okay, that's not what I wanted. Yes, there is one question. That's good.
I guess we didn't have any homework problems on interconnects, so I was wondering what kind of type of problem you might see.
Oh, I see. You could see problems asking about trade-offs of different types of routing algorithms, for example. I mean, one thing that comes to my mind right now, I'm not promising it's going to be on exam or anything, but it could give you a network type. It could give you the buffering. It could ask you to calculate the number of buffers and then talk about the trade-offs on bufferless versus buffered routing, potentially. I don't know, I haven't constructed this question yet, so take this with a grain of salt, but this gives you an idea. And also, the network topology is another example, right? We've covered a lot of network topologies, and they have different types of trade-offs in terms of the number of routers that require, for example, that they require in terms of the latencies. in the topology, in terms of router complexity, radix. So there might be questions like that. I don't know. But that sounds reasonable, right? Yeah.
There is a question. I mean, if you check in the website, last year final exam, maybe you already read it.
Oh, okay.
That can be a good sample.
That's true, yes. We had. Yeah, it may be good to look at past exams. It doesn't hurt, at least.
We didn't cover the round ahead and...
Yeah. So basically, yeah, you don't need to look at those. Clearly, we're not going to ask you questions on topics that are not covered in this course. Unless you want to. So run ahead. I think those topics we couldn't cover this time. We covered other topics like flash memory, for example, this time, but not... yeah, the topics that you have in the previous exams that are not covered in this course, you're not going to be responsible for. Yeah, this one, for example. Yeah.
So this question I asked myself a bit, is it like, would have been okay if this was like the big O notation, or?
Could you say it again?
Yeah, there was a question like how many links there are, like
Yeah.
in section B.
Okay, I see.
I asked myself a bit like, would it have been okay to have just dot down the big O notation?
Big O
or was
notation.
it really expected to calculate out?
No, I think you can calculate in this case.
Okay.
Yeah. We can calculate it. Big O would be easy. Well, easier, let me put it that way. Yeah, unless we say specifically put it in big O notation. It's not big O notation, yeah. But there may be some cases where the calculations are not, like the numbers are not perfect. In that case, as long as you show that you understand the concept and you get to the final equation, but you don't need to calculate the really final number necessarily, right? But maybe not in this. I don't think it's in this question. So there's a good cache coherence question, for example, here.
Here I was a bit confused because I think it should also be possible that the cache 2 to set 1 could also switch from invalid to exclusive.
Okay, I haven't looked at this question in a while.
Ah, okay.
So you think there's another way of answer?
Yeah.
To the first question. What is the inconsistency?
Yeah.
Like this part?
And I thought like it could be possible that like a set is just one is shared, one is invalid. There could be also possible valid state to begin with, and then it could switch
Yeah.
from invalid to exclusive.
So in the MESI protocol, okay, you're saying, no, let me answer the conceptual question rather than this one, because there may be people who may want to solve it.
Oh.
So you're thinking the same cache block in different caches can be in both shared. In one cache it could be in shared state, in the other cache it could be in invalid state.
Yeah.
Right. That is
There's
true.
like
Yes.
no bus messages which put the invalid to shared if like someone loads it.
Okay, so let me try to think about how it could happen. Right. You have two. So if you want to go from shared to invalid, the two cache blocks must have started in the shared state.
Yeah.
Right.
Yeah, there could be like a third cache that writes to it.
Yes, but then this cannot be shared.
Yeah, but then this one could like load it, and then they have both shared, and the third one could...
Yeah, so then now it depends on the protocol that's discussed in the class. I think the protocol that's discussed in class invalidates it.
Okay.
So basically, if the protocol is when you're writing, you update other caches, you're right. You could be in shared state. And also you need to update memory in that case, if you want to be in the shared state. Right. So in the protocol that's discussed in class, there is no shared dirty state, if I remember correctly. There's modified, there's exclusive, there's shared, and there's invalid. MESI.
Yeah.
Modified means basically it's dirty, and it's exclusive also, right?
Yeah.
Exclusive means it's clean, it's yours. Shared means it's really shared and clean. So according to that protocol, that cannot happen. What you said cannot happen. So it's really all about the protocol in the end. In some other protocol, what you said can perfectly happen, right? If I have a shared state where it could be modified and shared, and the memory is also up to date, sure. That's a good point, though. So if you somehow end up going down that rat hole during the exam, make sure you very, very clearly state your assumptions. Yeah. If, for example, you don't remember the protocol, as long as you can reason about and construct the protocol and tell us what the inconsistency is based on your assumptions, I think you'll get points for that. But if you write something down without explaining your assumptions, it's very hard to understand. Now I try to reverse engineer your assumptions right a little bit. It's easier when we talk, of course, but it's harder in a written exam. Does that make sense?
Yeah.
Think good? Okay. What else? Coherence is fun. Has anyone started implementing the last optional lab? I assume not, but no. Is anyone intending to do it for fun? Okay, that's good. That's good. Yeah, I know time is it's a concern, and that lab is the coherence part is the hardest part, as I mentioned. But if you like thinking about these things, then you'll have fun. Okay, what else? Any other questions that you may have? Any other topics? Let's see. We still have time. Yeah, I would definitely recommend solving that question and the consistency question. I cannot promise there will be questions on both, and we didn't cover prefetching, although this is a nice and easy question, I think. Okay, let's go back over here. It's a bit slow. And I came here from here. Okay, what else? Any other thoughts? Any other questions? Maybe not related to the exam. Well, we won't see each other again in a session at least. So if you have any questions on architecture, any topics related to the course, you can ask now. I know you're under exam pressure right now, so this may not be the best time to ask questions, but you can always contact me. Feel free. Like if you want to TA a course also in the future, if this is interesting to you, let me know. So now we have a real choice. Do you want to solve the branch prediction question, or do you want to go on a study? Up to you. So I'll be clear. You won't have a branch prediction question tomorrow. But Geraldo is happy to solve it if you want. Let's take a vote. Who would like to have solved right now? Who doesn't? Okay. Yeah.
Oh, I had a question, but I forgot it. Sorry.
Okay. About branch prediction?
Oh, right. How is the grading of the final lab going to work? Does it have a common deadline with the other labs, or are the other labs first going to receive a grade and great distributions and everything, like how will that be handled?
Why is it specific to the final lab?
Because it has such a late deadline.
Oh, you mean the bonus lab?
Yeah, the bonus.
Oh, bonus lab, yeah. I think bonus will, we're more flexible on the bonus. So if you actually do a good job on the bonus, you're likely to get a lot of credit. So I don't know what the deadline we stated was, do you remember?
The deadline is January 15th. Because as you know, you can submit until, I think that the cutoff date is February 1st.
Yes. So you can submit any lab until February 1st. But yeah, I wouldn't be too worried about the distribution or anything. If you do a good job with the bonus, that's good. Attempting it is also important. But yes, it'll be, I think in the end it'll be similar to the other labs. But we'll be more lenient on the bonus, for sure. Any other questions? So you're thinking of maybe doing the lab, I guess. That's good.
I wish I could. I'm not sure it's possible.
Depends on how you define doing it, I guess. Attempting it is possible, I think, but getting the latest bugs out may not be possible. These are some of the buggiest parts of processors, actually. If you look at coherence, consistency, if you look at the errata of processors, I don't know if you ever examined the errata. These documents where in the hardware reference manuals, basically, processor vendors talk about what are the known, essentially, errors with the processors. And a lot of them are related to coherence states. Basically, if under some, they don't of course give you a lot of detail, because these could potentially be security vulnerabilities too. If someone actually figures out how to exercise them, they could lead to security issues. That was one of the projects that we were thinking about doing when I was at Microsoft Research about 10 years ago. But these errata documents are actually relatively vague. They say under some certain conditions, you may move from this state to this other state, which is completely wrong. And as a result, you may actually get a halt in the system. Or you may get data corruption. Some of them are even more serious, but they don't actually tell you exactly how serious they are. These are things that are discovered after the fact, of course, after the thing is manufactured. And they have to document it. And they cannot fix it, because and some of them get fixed, of course, over time, potentially, if they figure out how to fix it while in the field. If there is enough catchability, if they can change the instruction sequence, for example, somehow, if you can detect the pattern, you can change it in the microcode potentially with microcode updates also, or software updates. But some of these things are not possible to fix. And if you look at those errata, a lot of them are related to consistency, coherence. We've actually done a lot of studies. We had a paper in Micro in 2008 that talks about these hardware bugs, RTL bugs. And usually whenever a new feature is introduced, that feature tends to be quite buggy. And we've done these studies of errors seen in Intel processors. Whenever they introduced virtualization extensions, for example, the number of bugs increased. And then it became reduced and then stabilized for some time. And whenever they introduced some other feature, the number of bugs increased again. Kind of similar to software development also. In the end, it's all the same software, hardware. It's a span. So basically it's not easy. This lab is the easier part. having a real system coherence protocol is not the easiest part. That's why people are trying to also get rid of coherence as much as possible, if you can do it, of course, right? And the states that we've seen, that we've given in this lab, there are only 4 states. In most systems today, Moisey is used, so it's at least 5 states. But if you want to avoid the race conditions, you need a bunch of intermediate states. And that's where the bugs are. If you forget an intermediate state in a transition, because there's a signal coming in and you cannot transition directly from one state to another before doing something else, and you forget that state, then essentially you get the wrong data, potentially. I think it's good exercise, especially if you're excited about these things. Yeah, we used to give this lab in the undergraduate architecture class at CMU. This was number 7, I think. Usually half of the class attempted it. And what goes to attempted, there are quite a few that got it correct. It's a bit intense. But if you're excited about it, I'd recommend attempting it. Anything else? Any other question? Thoughts? You may have a question. One more? No? Okay. Okay, then we can part. Feel free to email me anytime. But good luck on the exam tomorrow. Hopefully it'll be fun. Hopefully you'll learn something from the exam. That's the most important part. Okay. See you later.